angular and linear velocity. Again, we're talking about this rotating vector. So the green line that I'm talking about here could be our vector, which is then rotating. Again, we talk about positive being anti-clockwise. The size of our vector will have a consequence. That gives us a larger or smaller circle being subtended here as this thing rotates around. But remember, in terms of radians, it doesn't matter how big the circle is that's going around here, the angle will always be the same, okay, in radians. So we start off by considering 1. So the vector is unit length. And then we'll talk about later what the consequences of that being more or less than 1 is. So for now, 1. Rotating round. If we think about what linear velocity is, linear velocity v for linear velocity is given by v equals displacement over time, a familiar formula to you, I hope. Displacement over time, we tend to use the letter S for displacement. So in that sense, S is the same as we were talking about with the radian. The arc length S is the displacement, the physical displacement. It's moved from one point to another, measured in meters or centimeters, something like that. So the linear velocity is the displacement over the time. Displacement is actually it's a vector equivalent of distance. So distance is got size only, like I'm going 3 meters or 4 miles or something. If I want to measure the displacement, I not only have to give the magnitude but also the direction. So I'm going 4 miles at 40 degrees from north or something like that, giving a bearing. So we're talking about the vector idea here. So linear velocity, displacement over time. There's an equivalent thing that we define when we talk about rotation. So instead of talking about a linear velocity as something's moving, we talk about an angular velocity as something's moving through a given angle theta. And we talk about the angular velocity and use the symbol omega to represent that. So this symbol here, omega, represents angular velocity. And just like linear velocity, angular velocity omega is given by omega equals angle over time. So it's equivalent concept. Angular velocity, we're talking about things rotating, and that's just a measure of the angle we've turned through divided by the time it took. Linear velocity, the physical distance we've moved, displacement over time. Unit, what do we measure velocity in? Meters per second, common unit. What about this? What would this be in? No? What would we measure the angle in? Not in angle, not in radians yet. Radians per second, yes. So we measure linear velocity in meters per second, angular velocity in radians per second. What angle have we turned through per second? The rate at which we're rotating, angular velocity. Frequency. There's a relationship between angular velocity and frequency that we're going to talk about now. Frequency, if you remember, is the number of turns per second, isn't it? It's the frequency of something is the rate, number of turns it goes through per second. Something that I think you're familiar with, measured in hertz. So with a frequency of number of turns per second. If we think about the angular velocity for a minute, we can see that there's a relationship between the two. If I consider this thing rotating round, remember the angular velocity is the angle it turns through divided by the time we took, but the angle it turns through per second. If the frequency is the number of turns per second, then if it's got a frequency of 1, that means it goes through 1 complete revolution in a second. So what angle has it gone through in a second? What's 1 complete turn in radians? 2 pi. 2 pi radians. So the angular velocity would be 2 pi radians per second if the frequency was 1, wouldn't it? If the frequency was 2, then it would go through 2 complete turns in a second, and that would be an angle of 4 pi radians per second. So to get the angular velocity, all we do is multiply the frequency by 2 pi. Yeah, and we get a formula that relates to 2. We've got that angular velocity equals 2 pi, which is 1 turn, multiplied by the frequency, which is the number of turns per second. So we get this relationship between the angular velocity and frequency of rotation. And that relationship is used a lot when we talk about AC theory. If you've not talked about that already, you might have done. The relationship between the angular velocity and the frequency. Now, if we consider again our rotation, okay, I want to know this point, literally how far has it moved. So I'm after its linear velocity now, which is the distance it's travelled around this circle per second. So I'm interested in the actual distance it's moved. If we think about what the rotation is, 1 complete rotation, that's the circumference of the circle. What's that? What's the formula for the circumference of a circle? No. 2 pi, no. Pi d or 2 pi r. 2 pi r, circumference of a circle. Yeah. Yes. 2 pi r. The distance travelled is 2 pi r. Now, if the frequency is 1, what's the total distance it's travelled in a second? 2 pi r. 2 pi times the radius. Agreed? Whatever that radius is. If the frequency is 2, 2 pi r times 2, and so on. So the linear velocity is 2 pi r times the frequency. But we know that the angular velocity is 2 pi times the frequency. So can you work out what the equation is that relates the linear velocity and the angular velocity? Yes. If the linear velocity is 2 pi r times the frequency, what's the relationship between omega and that? Yes, linear velocity equals the angular velocity, which is 2 pi times the frequency, times the r. The only thing that was missing was the r. So we've got another relationship between the linear velocity and the angular velocity. V equals omega r. Those are 2 very important formulae. Okay, question. Have a go at this. Number 1. A flywheel rotates at a rate of 3,600 RPM. RPM? Revolutions per minute. If it has a diameter of 3.68 meters, find the angular velocity and the linear velocity. I'll just pause and let you have a go at it. So, part A, omega equals 2 pi f. The key is the frequency is number of cycles or number of turns per second. So divide by 60 to get the frequency is 60 hertz. So the angular velocity is then 2 pi times 60. Leave it in terms of pi. You can do that. That's an exact answer. And sometimes, as we'll see, it's useful to leave it in terms of pi. So the answer is either 120 pi radians per second or 377 radians per second to 3 significant figures. 3 significant figures is appropriate given the values that we're going to put in. Part B, once we've got the angular velocity, V equals omega r. So again, 120, again r is half the diameter, so that's 1.84 meters. Putting the values in, we can then leave it in terms of pi again, or we can come up with the final answer of about 694 meters per second, again to an appropriate accuracy. So question number 2, you've got a vector that's rotating. Its size 3.2 newtons. So that's like your radius of rotation. That's your force vector. It rotates so that it moves to a distance of 138 meters in 1 minute. Find the linear velocity from the definition of linear velocity. And from that you can find the angular velocity, omega, and then once you've got that you can find the frequency of rotation of this thing. Okay, so this question then, the solution A, velocity is distance over time. This is the formula. The definition of linear velocity is displacement over time. So 138 over 60 gives us 2.3 meters per second. The formula that relates linear velocity and angular velocity is this. So rearrange for omega, v over r, and we get 0.73 radians per second. C, the relationship between omega and frequency is this. So divide by 2 pi and we get frequency equals omega over 2 pi, which gives us 0.114 hertz. Okay.